This chapter is all about chemical reactions. We're going to learn some more basic concepts of chemical reactions and be able to classify a few, not too many, classify a few different types of chemical reactions.
In these next few slides, we're going to learn a little more information about reading chemical reactions and some of the beginning steps towards writing chemical reactions. If you remember, chemical reactions can also be called chemical equations, and what's on the left-hand side are called the reactants. So if this is our reaction, and this is trying to show a glucose molecule reacting with oxygen molecules, these are the reactants. We separate the product side from the reactant side with some sort of arrow, but over here are the chemicals that are being produced. So these are the products. So here's kind of a picture of a chemical reaction. If we were going to write this, given the above information, we would write the formulas of the chemicals. The formula for glucose, you don't have to have this memorized, but it's C6H12O6, and the formula for oxygen is O2. We put a plus between all the chemicals that are reacting, and we also put numbers before the formula to say what's the ratio. And from the above information, it's 1 glucose for every 6 oxygen, so we'd put 6 there. On the product side, there's carbon dioxide molecules and there's water molecules, and we'll put a plus in between them. And just for this reaction happens to be that for every 1 glucose that reacts, there's 6 carbon dioxides and 6 water molecules that are produced. When you have chemical reactions, this is the basic part. You have to write the formulas, an arrow, and pluses between the chemicals and how many chemicals are reacting. You can also add additional information, and some additional information are those subscripts that we mentioned earlier. You can state what phase the chemical is in. AQ means that it's a chemical that's dissolved in water, and it doesn't have to be an ionic compound, it could be any compound. On these next few slides, we're going to learn about a process called balancing a chemical reaction. From the information we learned previously, we know that atoms aren't created or destroyed in a chemical reaction. It's only electrons that move from one atom to another or move closer to the nucleus or a little bit further away. Bonds could be broken, but we don't create or destroy the nucleus of the atom. Often when we have new chemical reactions, we have the formulas for the reactants and products, but we're not quite sure what's the ratio. And getting the correct ratio of molecules, this process is called balancing a chemical reaction. On the next page are some general guidelines for getting this done. The main thing you need to do, and there's really only one right answer, is to figure out what number goes in front of the formulas for the various chemicals. So in this particular example, this is a carbon-based molecule. It's called nonane. This is actually the average molecular formula for gasoline. Gasoline's a complex mixture, but on average, for every carbon-based molecule, there's about 9 carbons and 20 hydrogens. The reaction in your engine, it's a combustion reaction, and oxygen is reacting. But the question is, what's that proportion? How many, for every 1 nonane molecule that reacts, how many oxygens are reacting? That proportion is pretty important for someone who's tuning your car. How much gasoline is being injected into the reaction chamber and how much air containing the oxygen gets mixed in there. It's pretty important that you have the right ratio. So let's look at the general guidelines on the next page. And these are general. Some of you may be able to look at the reaction and just put the numbers in front and you get it. You can see it. Here are some guidelines to help you keep track of when you make changes. So what's the first thing we should do? The first thing is to make a list of the atoms on the reactant side and the product side, and how many atoms on each side do you have. So if we go back and look at our reaction, we can see the various chemicals. And when we look at those, we can see how many atoms of each are on both sides. If we look at the reactant side, there's carbon, there's hydrogen, and there's oxygen. On the reactant side, there's 9 carbons, there's 20 hydrogens, and there's 2 oxygens. On the product side, you should have the same type of atom, so there's carbon, there's hydrogen, and there's oxygen. There's 1 carbon, there's 2 hydrogens, and there's 3 oxygens. Oxygen occurs in both molecules, 2 in carbon dioxide and 1 in water, so a total of 3. There's not one way you have to do this. Again, some of you may have different ways to get to the same place and you'll get the right answer. But usually when you start looking at the atoms, start with the atom that occurs in the least number of molecules. We'll see in just a second, that'll make it a little bit easier. As far as what you're supposed to do during the balancing process, we're going to put whole numbers to the left of the formula of a chemical, and that means you have that many of that whole molecule. And when you do put numbers, then you're going to recount. So when we go back, which chemical are we going to start out with? We're going to try and fix carbon, hydrogen, or oxygen first. And this is, again, just a guideline, but we'll look at number 2. I'm going to make another list of the atoms. Again, you don't have to, but we're going to. And we're going to do something called the occurrence. How many molecules does that atom occur in? And we'll count on both sides of the equation. Not how many total atoms are there, but how many molecules does it occur in. So we're going to look at occurrence. Carbon, if we look at it, occurs in nonane on the reactant side and carbon dioxide on the product side. So it occurs in 2 molecules. Hydrogen also occurs in nonane and it occurs in water, so it occurs twice. Oxygen occurs once in 1 molecule on the reactant side, but in both molecules on the product side. So it occurs in 3 different molecules. It occurs in the most molecules, so it's kind of the hardest to keep track of. So we're going to save oxygen for last. So we could either start with carbon or hydrogen first. We'll start with carbon first since it's up top. So the next step is to add a whole number in front of a molecule. So we're looking at carbon. There's 9 atoms of carbon on the reactant side. It occurs once on the product side. So what are we going to do? Well, we need if we had one of these molecules, one nonane molecule that has 9 carbons, every carbon in there forms a carbon dioxide. It occurs once per molecule there. 9 carbon atoms would form 9 carbon dioxide molecules on the product side. 9 times 1 for carbon is 9. So we'll cross off the 1 and write a 9. But that also changed the number of oxygen atoms. Okay, so 9 carbon dioxide molecules, 9 times 2, this would give us 18 oxygen atoms. So 9 carbon dioxide molecules, that's 9 carbons and 18 oxygens. So we need to recount the number of oxygens too. We made a change. If you weren't anal and you just added 18 to 3, you'd get the wrong answer. So when we look at it, there's 18 oxygens from 9 carbon dioxides, and there's still that 1 that's in 1 water molecule. So our answer would be 19. Okay, so now carbon looks good. It could change, you never know, but there's 9 carbon atoms on both sides. Now we're going to do hydrogen. Still going to save oxygen for last. So what do we see? There's 20 hydrogens on the reactant side, 2 on the product side. We need to have enough water molecules so that we have 20 hydrogen atoms. Hydrogen occurs twice per water molecule. So if we had 10 water molecules being formed, 10 times 2, that would change that number to 20. However, there's oxygen in water, so we have to recount oxygen again. And again, in most disciplines, it's good to be anal. If you just added 10 to 19, you'd get the wrong answer. How many oxygens do we have? Well, we still have the 18 from 9 carbon dioxide molecules, and we have 10 from the 10 water molecules. So 10 plus 18 is 28. So now we have the same number of hydrogens on both sides. Oxygen is next, and we've saved it for last. Currently, we have too many oxygens on the product side, 28. How many O2 molecules would have to react in order to have 28 oxygen atoms reacting on the reactant side? It occurs twice per molecule, so if there is 14 molecules of O2 reacting, it changes the number of oxygen atoms to 28. There we go. This is our balanced chemical reaction. And what does it tell us? If we made a molecule-to-molecule relationship, for every one nonane, there's 14 oxygens that react. And for every one nonane molecule, 9 carbon dioxides are formed. So for any chemical reaction, once you get it balanced, you can make relationships, a number relationship, between how many molecules are reacting and how many are being produced. And someone who's tuned the car, this is a pretty important piece of information. Or maybe someone who's analyzing how much carbon dioxide is being emitted into the environment could use this piece of information. If you knew how many gallons of gasoline were being used per year, you could figure out how many, and we'll learn how to do this eventually, you can figure out how many of these molecules are reacting, and we know there's 9 times as many CO2 molecules that are reacting for every one of those nonane molecules that are being used up. In this next part of the chapter, we're going to introduce you to some more chemical reactions. Well, we've talked about them before, we've done them before, but we're going to look a little closer at them. We're really only going to look at 3 main ones, and these 3 main ones, we're going to go beyond just being able to read it. We're going to decide if we had these reactions, would this type of reaction, would it occur? If we mix reagents together, could you have these type of reactions? So there's 3 main types, and it's a small part of chemistry. There's an enormous amount of different types of chemical reactions. Here we're just going to look at 3 relatively simple type of reactions. The first one we're going to look at, they're called precipitation reactions. And they're part of a general class of reactions called double replacement. And I'll kind of explain why it's called double replacement. The second type are acid-base neutralization reactions, which are also under the umbrella of double replacement. The last type is called oxidation reduction reactions, also called redox reactions, and for some odd reason, single replacement. But we'll try and grasp why they get that. All of these reactions we've done in the laboratory before. Some of them you did in the first laboratory. Here's the calcium chloride sodium carbonate one once again, and remember it forms a solid, and it forms an ionic solid, and it's called a precipitation. Remember we said that solid is called a precipitate. Precipitation reactions, the ones we're going to deal with, it's when you mix 2 aqueous ionic compounds together, and if there's a cation and an anion, form a really strong ionic bond and form a crystal that's insoluble. That's a precipitation reaction. For the precipitation reactions we're going to look at, if we look at our example up above, there's 2 reactants, 2 products, and that'll be the case for all the ones that we look at. Also note, when these reactions occur, it's between ions. There's no change of the ionic state of the ions. So there, in this example, there's calcium ions on the reactant side, there's calcium ions on the product side. On the product side, there's an ionic bond that forms between the calcium and the carbonate, and that's what's driving the reaction. But the ions, same ions on both sides. This is called double replacement reaction. And if you kind of look at it, if you look at the reactant side, this calcium metal cation and this sodium metal cation, they switch partners. So the calcium goes with the carbonate and the sodium goes with the chloride. And that's why it's called a double replacement. The next type we're going to look at is an acid-base type of reaction. And the one we're going to look at right now, there's other types that we'll eventually learn about. But in this type, it's an acid that's reacting with a hydroxide salt. So it's an acid, and you have a table of acids in your information packet, but it's an acid that's reacting with a hydroxide. When we do this particular reaction, and if we look at it, if we wrote the ionic equation form of the reactant, so on the reactant side for the hydrochloric acid is a strong acid, we have hydrogen ions and we have chloride ions. In the other container, so before they're mixed, they're in different containers, we have sodium ions and we have hydroxide ions. When this reaction occurs, the hydrogen ions collide with the hydroxide ions, and eventually we make H2O. HOH, H2O, we make water. The sodium in this example and the chloride in this example are just spectator ions, so they're still over there. They're still the same form. In the acid-base neutralization reactions, in which it's a hydroxide salt, hydroxide ionic compound, we always form water. But it's also called double replacement. It's different than the precipitation type. But if we kind of looked here, this sodium and that H, they switch partners and we form the other two products on the other side. Two reactants, two products for precipitation reactions and acid-base reactions. The last type, the redox reaction, if you look at the examples we're going to look at in the beginning, it also has two reactants, two products, but it's a little different for this type. We've done this reaction. In this one, it's elemental zinc reacting with an aqueous solution of copper sulfate. So we have elemental zinc, so Zn, and we'll just emphasize it with a naught, that it's in its elemental state. We have copper 2+, and we have sulfate. In this reaction, the copper collides with the zinc, and in an oxidation-reduction reaction, there's a transfer of electrons between two different reactants. And in this particular example, the copper cation takes enough electrons away from zinc to go to its elemental state. Anytime there's a transfer of electrons from one chemical to another, it's called a redox reaction. In this particular example, it's a reaction between a metal and a metal cation. It doesn't have to be that way, but these are the type that we're going to learn about in this chapter. We'll learn about other types, but this is the particular type you're going to be able to predict if a reaction happens or not. If we look at what's formed on the product side, notice for copper, it's in its elemental state. So in this particular reaction, copper took enough electrons to go to its elemental state. We see over here with the zinc sulfate compound, that's part of an ionic compound, that zinc lost some electrons. It's a cation. And if we looked deeper at that formula, that's zinc 2+. Sulfate, still sulfate. Sulfate, it's a spectator. Whoops, forgot our 2 negative over there. It's sulfate on the reactant side, it's sulfate on the product side. The redox reactions we're going to be looking at and predicting whether they occur or not will have this general format. The anion is going to be a spectator, and the two metal species react. And the ones we're looking at, it'll be a metal cation with a metal atom that's in its elemental state. All the redox reactions that we're going to be able to predict, the metal cation, if it is able to take electrons, would take enough to go to its elemental state. It's not always that way, though. For example, iron 2+ and iron 3+, they're part of molecules in your body. This reaction happens all the time in your mitochondria, where the iron 2+ and iron 3+, it goes between those states in some different reactions. That's a redox reaction. You can save that till your time in biochemistry. And here we're going to start with some pretty straightforward ones. And it has this general format. We're also going to be looking at combustion reactions. Oxygen is really good at taking electrons away from other types of chemicals, and we'll look at those a little bit later. But for right now, These are the three basic ones. And if I gave you the reactants, one of the main things you need to be able to do is to recognize what potential type of reaction it could be. And if we look at it, precipitation, if you saw two aqueous ionic compounds, that's a potential for a precipitation reaction. Acid-base neutralization reactions, if you had an acid plus a hydroxide ionic compound that's dissolved in water, that's a potential acid-base neutralization reaction. Oxidation reduction reactions, it's a single atom plus an aqueous ionic compound. It's a metal plus an aqueous ionic compound. We're going to practice these chemical reactions on the upcoming pages. There's a lot of information here, but the best way to learn them is to practice and to listen as we're presenting the example problems. So we'll have a lot of fun. In the next section of this chapter, we're going to go over guidelines for predicting whether a reaction will occur or not. And these reactions could be double replacement, single replacement, oxidation reduction, precipitation, acid-base reactions. In these reactions, I'm going to give you reactants, and you're going to decide, well, if I mix these things together, would I have a chemical reaction, or are we just mixing things together? In order to do this, if you are given the reactants, first you have to know what are the potential, or what is the potential reaction that could occur. So you need to be able to recognize, if I gave you the reactants, which potential type could occur. If you do predict that one does occur, the next step after that is to decide what can be formed. So we need to write down the formulas of the chemicals that would form if a reaction occurred. Once you write down the correct formulas for the products, once you have the correct formulas for the products that are formed, one of the last steps is to balance the chemical reaction. And balancing and getting the correct formulas for the products are two separate things. You can't combine the two and do them at the same time. And that statement will become clear when we actually go through some examples. But that's one of the biggest common mistakes, to look at the reactants and make the products and balance the number of atoms at the same time. The problem wants you to, and it says within the problem, you also have to indicate what phase it's in. The first type of reaction we're going to look at to try and predict if one would occur would be precipitation type of reaction. In a precipitation type of reaction, the potential reactants are two salt solutions. And shown below is an example of a precipitation reaction occurring. And it's actually showing the result. In each beaker, there were two salt solutions. Water is the medium in which the reaction's occurring, but it's the dissolved solvated ions that collide and react and form the crystal. You have a precipitation type of reaction from two salt solutions when you mix a cation and anion together, and there's a super strong attraction, and they start sticking to each other, and a crystal starts forming. This super strong reaction is directly related to solubility. And we're going to show you a solubility chart that's going to help you predict if a reaction would occur or not. You have a precipitation reaction when the cation and the anion that come together are insoluble in water. So let's examine the first reaction. In the first reaction, we're mixing a solution of calcium bromide and a separate solution of sodium hydroxide. In this container of calcium bromide, it's aqueous. The calcium and the bromide ions are both solvate and soluble, moving around independently. In a different solution, in a different container, like a beaker or a dropper bottle or whatever, there's sodium and hydroxide ions, solvated ions that are moving around. When we mix them together, so let's draw a picture of this process. We have a beaker or a container of calcium bromide, so that's what we're showing right here, some aqueous solution, so there's water in there, solvated calcium ions, solvated bromine ions. In a separate container we have solvated sodium ions and hydroxide ions mixed with water. When you add those two together, so this is like your first laboratory where you took dropper bottles of two salt solutions and put them into your test tube. When the cations from one container get mixed with an anion from another container, is there such a super strong attraction that a crystal starts forming and you form a precipitate. So when we compare, we need to compare calcium from this one and hydroxide from the other one when they're mixed together. You wouldn't compare calcium and sodium. Their cations are both positive. They would repel each other. So you have to compare a cation from one to an anion for the other. And you do the same thing with the sodium. When it's mixed with the bromide in another container, would a precipitate form? Here in this middle containers, the comparison when they're mixed together. So where do we go to figure out is it insoluble or not? And we go to our information packet. I mean, we could memorize it and memorize trends, but here's a solubility chart. And you'll use this to compare to determine if that ionic compound is insoluble. If it's insoluble, then it's forming a solid. If it's insoluble, then a chemical reaction happens. So let's see how we use this chart. It's a table, and there's S's, there's P's, there's I's. What do we see up here? S, if you see that, that means soluble. Hopefully you don't ever get one that has P or D. The ones we should ever get for examples are S or I. I means insoluble. So how do we use it? Well, we find a cation, and an example could be aluminum, and down this list are all the cations. Up here are all the anions. So if you wanted to compare calcium and acetate, where they intersect, S means soluble. It means where aluminum and acetate would be soluble. If you mixed aluminum with oxide, there's the I. Those two, if they came in contact, they were solvated and came in contact with each other. I means insoluble, means a precipitate would form. I on this chart means that a reaction will happen. I on this chart means it forms a solid. S on this chart means those two ions, that cation and the anion, are soluble, and they don't form a precipitate. Soluble on this chart means S. On a chemical reaction, here's a little bit of the confusing part. That if we were going to label that ionic compound, it would be labeled AQ. I on this chart means insoluble, means it forms a solid, means it forms a precipitate. How would we label it on the chemical reaction? S's, there's a lot of S's in words. On the chemical reaction, it would be labeled S. S on this chart means soluble. If it's S on this chart, it's AQ on the chemical reaction. I on this chart means it's insoluble, and that means a reaction is occurring. And I on here, if we're going to give a phase label on the chemical reaction, would be S for solid. So let's go back to our lecture notes and look at what ions we need to compare. So the first one, we need to compare calcium and hydroxide. So here's calcium, a listing for its period. Hydroxide is right here, and we go down it. And the intersect is I. I means if those two ions came in contact, they would form a crystal. They're insoluble, meaning a chemical reaction would happen because of the fact that calcium hydroxide is insoluble. Let's also look at sodium and bromide. When we label sodium and bromide on the other side of the equation for the product, are we going to label it AQ because it's still soluble, or are we going to label it S because it forms a precipitate? You could have a circumstance where they both form solids, but let's go check out sodium and let's go check out bromide, that combination in our information packet. So if we just found sodium and just kind of went across, S, that's strange. Yeah. Sodium is a group 1 cation, and group 1 cations in general, there are very few precipitates that form with those. A 1 plus cation, that attraction to other anions, 1 plus is weaker versus a 2 plus cation. And in general, group 1 cations don't form precipitates. And if you went looking at potassium and went across, you'd see a lot of S's with it too. We could go down from bromide, but we already know sodium's soluble. So the sodium and the bromide soluble, meaning on the chemical reaction, as far as a phase label, we're going to label it AQ. So that whole process was just to figure out predicting that a reaction will occur. A reaction does occur, so we're going to form some products. In a double replacement, you have two reactants, you form two products. And like we mentioned earlier, the cations and the anions switch partners. So we're going to make a product of calcium hydroxide, and we're going to write a product of sodium bromide. When you write the two products, it doesn't matter if you write the sodium bromide salt first or the calcium hydroxide salt first. As long as you get the right formula of the compound, it doesn't matter. And again, I know in English when you write a sentence, it matters the order. It doesn't matter in chemistry. So if we're looking at our general guidelines on the previous slide, we're on step 4 currently. So there's the formula for calcium hydroxide and sodium bromide. And as I mentioned earlier, don't combine writing the formulas for the products and balancing the equation at the same time. Sodium's 1 plus, bromide's 1 negative. It's a 1-to-1 ratio. It doesn't matter that there's a 2 over here on calcium bromide. You don't carry that 2 to the formula of sodium bromide. It's a 1-to-1 ratio. You figure it out based upon the charges. When we balance the chemical reaction, yeah, we need to have the same number of atoms on both sides, so that 2 will be important in balancing, but not making the product. There's 1 hydroxide in sodium hydroxide. It's a 1 negative and sodium's a 1 positive. But for calcium hydroxide, there's 2 hydroxides for every 1 2 plus calcium ion. So for the calcium hydroxide, it's the insoluble one, it's the precipitate, so we get an S. S on the chemical reaction means solid. Sodium bromide is still soluble, so soluble means AQ. As far as balancing, you could make a list, but sometimes you can just visually see and figure out what it should be. There's 2 bromides in the calcium bromide on the reactant side, so putting a 2 there makes it so we have 2 bromine atoms on the product side. There's 2 hydroxides in calcium hydroxide on the product side, so putting a 2 there makes 2 hydroxides. But now it creates 2 sodiums, but we already had 2 sodiums over here. This is our final answer. A balanced reaction with the reactants and the correct formulas of the products with the correct phases. Okay, so here's another one. 2 salt solutions. It's a potential precipitation reaction. Go ahead and pause the video and predict if the reaction would occur. And if a reaction does occur, 2 reactants, 2 products, write the correct formulas of the products and make sure you write the correct phase label and make sure it's balanced. The balancing is the last thing you should do. So go ahead and pause the video. So shown below are the formulas of the 4 ions that are being mixed together. So we need to compare when lead is mixed with iodide. Would there be a precipitate? And would a precipitate form when potassium ions are mixed with nitrate ions? So we'll look at our information packet and see if we see I. If they're both S, then it's no reaction. We're just mixing 2 salt solutions. If one of the combinations or both of them have I, then a chemical reaction happens. If we look at potassium and nitrate, and if we compared, potassium's just like sodium, it's a group 1. S's all the way across. When potassium comes in contact with nitrate, there's no reaction. In fact, if you went down from nitrate, it's another one that as you go down, I don't see an I all the way down. There's some decomposition reactions, but we're looking for I and we don't see it. Nitrate salts are very soluble. Group 1 cation salts are very soluble. And if you have those, I mean, you'll deal with these enough that you'll get to know that you don't even have to use the solubility chart. So let's look at that lead and iodide combination. If we look at lead, there's some S's and I's. It depends what anion it's mixed with. If we find iodide and go down, oh, There we go. It's I. I meaning it forms a precipitate. I meaning a reaction occurs. So we'll go back to our lecture notes, create the two products. Make sure that the formulas of those ionic compounds are correct, and then we'll have the correct phase label, and then lastly we'll balance the chemical reaction. So as far as writing the correct formulas of the products, shown on the right, two reactants, two products. I've grouped the cations and anions together, the lead and the iodide and the potassium and the nitrate. Potassium is a 1 plus ion, nitrate's a 1 negative, so a 1-to-1 ratio. So how it's written on the left-hand side, potassium nitrate. Lead and iodide, lead is a 2 plus cation, iodide is a 1 negative, so we need 2 iodide anions for every 1 lead cation. And again, don't look at the reactant side to write the product formulas. It doesn't matter that there's 1 iodide per 1 potassium on the reactant side. You have to look at the charges of the cation and the anions that are coming together. So PbI2 is the correct formula. As far as phase labels, potassium nitrate was soluble, so it gets the AQ. Lead iodide was the precipitate, so S for solid. As far as balancing, it needs to be balanced. There's 2 I atoms on the product side, 1 on the reactant side. And again, we could make tables, but we can visually look at it. 2 of those potassium iodide compounds, and now there's 2 potassiums on the reactant side, so putting a 2 there. 2 potassium nitrate compounds on the product side, but now there's 2 nitrates, but oh, that's good. We already have 2 nitrates. So there's our complete balanced chemical reaction with phase labels.
On the next page, we're going to learn about the different formats that we can write chemical reactions in. So here, this is a complete balanced chemical reaction. It's called a molecular equation. On the next couple pages, we're going to learn about ionic equations. It says the same thing, just a slightly different form.
When we look at this chemical reaction, you can look at it and look at what phase the chemicals are in, and it paints a picture of the physical process that is actually happening. If we look at the calcium chloride portion and its AQ, if this was in a beaker or in one of your dropper bottles, so over here is a beaker, what would it be like? Well, AQ means the calcium and the chloride ions are actually solvated. I mean, this equation, you put them together as a formula of a compound, but in reality, it's individual calcium ions and individual chloride ions that are within an aqueous mixture. So there'd be calcium ions and chloride ions that are solvated, and there would be lots of H2O molecules surrounding and part of the medium of this mixture. In the sodium chloride AQ, this reactant, in that dropper bottle, or you can think of it as test tube or beaker or whatever, it would have individual solvated sodium ions and individually solvated carbonate ions. And there'd be water that's part of that mixture. This is actually a reaction you did in your first laboratory. You had a 10% calcium chloride solution in a dropper bottle and a 10% sodium carbonate solution in a dropper bottle. You put both solutions in the test tube, and when you mix them together, you form that white precipitate. That white precipitate was a crystal of calcium carbonate that was growing, and that's what we see on the product side. Calcium carbonate S. S means solid. So that's the white solid that was growing. The sodium and the chloride, they collided, but they didn't stick to each other. And the sodium and the chloride were still AQ. That 2 plus calcium ion and that 2 negative carbonate ion, the larger the charges in general, the stronger the attraction. When those two came in contact, when you mix them together, that strong attraction between the calcium and the carbonate is the reason why that crystal started forming. So we'll keep drawing a picture and show that these two were mixed together into a larger beaker. And in that larger beaker, the calcium and the carbonate would form the solid. The sodium ions and the chlorine ions were still AQ. And water is just the medium in which the reaction is occurring, so there'd be lots of H2O molecules. Written like this for the equation, it's called a molecular equation. And that's showing the formulas of the ionic compounds, how you would expect so far as you've went through this class. In reality, they're really not together when the subscript says AQ. They are if it's solid, but not AQ. There's a different way of writing this chemical reaction, and it's called an ionic equation. An ionic equation and a molecular equation tell you the same thing. The ionic format is just slightly different. So let's give an example of how it would be different from a molecular to an ionic. So molecular and ionic equation. And for example, if you had sodium chloride, NaCl, and that was part of a molecular equation, if the subscript was AQ, that tells us that they're individual solvated ions. Well, for an ionic equation, you write the formulas of the ions with their charges. So you'd write sodium plus and chloride and put a plus in between them. And writing it like this says the same thing as AQ. Writing them as individual ions is saying that it's an AQ solution. So it's just a different format. It means the same thing. Another example could be the calcium chloride. It's AQ. So in reality, they're physically separated in space, solvated ions moving independently in the aqueous solution. For the ionic equation form, you would write calcium and chloride ions and put a plus in between them. But there's two chlorides, and we're not going to get rid of, so there's two in the formula. We're not going to get rid of a chloride ion by writing it in ionic, but you don't put it as a subscript on the chloride ion on the ionic equation. You just say that there's two chlorides that are moving around. If in the molecular equation the ionic compound was a solid, like silver chloride S, well, for the ionic, you don't change it. It's still, you don't separate them, you keep them together. And being together says it's a solid. Those ions are together forming a crystal. What if in the molecular equation, what if there was two calcium chlorides and it was AQ? When you create the ionic equation from the molecular equation, you still have calcium, you still have chloride, so we'll write the formulas of the two ions. And then, you don't lose atoms, don't lose ions, you have to write how many of each are there. So there's two calcium ions in two of the calcium chloride compounds, and 4 chloride ions. So if we're given a molecular equation, what's the process for writing it in the other form? There's different types of forms, different types of ionic equation. The first one we're going to look at is how to write it, how to read a complete ionic equation. When we go from one form to the other, some things may change, some things may not. And the ionic compounds that have AQ are definitely changed. If you see a subscript that's a solid, or an L for a liquid, or a G for a gas, those don't change. So when we go down below, we have 4 different compounds. 3 out of the 4, we're going to change the format slightly. The calcium carbonate, so we'll make it our arrow for products and reactants dividing. The calcium carbonate, that doesn't change. So we'll write calcium carbonate. Okay, the sodium chloride that's AQ, well, we're going to write those ions separately. So there'd be one for the cation and one for the anion. The sodium carbonate is AQ, so we're going to write the formula for the cation and the formula for the anion. And the calcium chloride, like we saw on the previous page, well, that's AQ. So we're going to write the formulas of the cation and the anion for both. So for calcium chloride, just like we showed on the previous page, there's the calcium ion, calcium 2 plus, don't forget the charge, and chloride ions. For sodium carbonate, there's the sodium ion and the carbonate ion, 2 negative. On the product side, for the sodium chloride AQ, there's the sodium ion and the chloride ion. Again, we're not losing atoms. We're not trying to say that it's a change of phase. On calcium chloride in the molecular equation, there's 2 chlorides per calcium. When we write it for the ionic equation, we don't put it as subscript. We put it out in front and say there's 2 chlorides for every 1 calcium ion in that solution. For the sodium carbonate, there's 2 sodiums for every 1 carbonate. So there's going to be a 2 out in front of the sodium. On the product side, 2 of the entire sodium chloride compound, so there's 2 sodiums and there's 2 chlorides. In molecular equation, you definitely have to have the phase to know what phase it's in. For an ionic equation, having the ions separated when you read it tells you that they're solvated ions. There's also something called the net ionic equation. If we look a little closer at exactly what's happening when we read our chemical reaction, what's happening, what's causing the process to occur, it's when the calcium and the carbonate, when they collide, they stick to each other and the crystal starts building. The sodium and the chloride, they're moving around in that solution, but it's such a weak attraction that they stay solvated. We see them solvated on the reactant side. They're same exact form on the product side. They're spectators. And that comes up with a new term. They're called spectator and they're ions, so they're called spectator ions. A net ionic equation, when you write it, you eliminate the spectators. And in this case, we're talking about these type of equations. They're called spectator ions. So in this particular example, this chemical reaction, the spectator ions are the sodium and the chloride ions. So there's sodium and sodium, and there's exactly 2. They cancel each other out. It's kind of like a math equation. That's why it's also called a chemical equation and a chemical reaction. So we're going to eliminate, when we go down and write the net equation, the spectator ions. 2 sodiums on the reactant side, 2 sodiums on the product side. 2 chlorides on the product side, 2 chlorides on the reactant side. So when we rewrite this for the net ionic equation, we'd write it as calcium 2 plus carbonate 2 negative forms the calcium carbonate. The net ionic equation shows exactly what's reacting. It eliminates the other ions that are just spectators. The next class of reactions that we're going to talk about is a class that's called oxidation reduction reaction, abbreviated as Redox. In this type of reaction, there's a transfer of an electron from one chemical to another. In any redox reaction, there's one chemical that's losing electrons, and there's one chemical that's taking electrons. When you have a redox reaction, there's a change of chemical energy, and this is analogous to a satellite moving around a planet. That satellite has potential energy moving around the planet, and it's based upon its position and the size of the planet. If another planet got closer, say a satellite was moving around the moon and the Earth got closer, the Earth could take the satellite away from the moon. And that potential energy of that satellite would be different on the Earth than it is on the moon. When you have a redox reaction, you have an electron moving in a chemical substance, and it has a certain potential energy. That's its chemical energy. That electron would move to another planet, and its potential energy, that chemical energy from that electron, would change. When you have a redox reaction, there's a few definitions and names of the chemicals that are losing and gaining the electrons. If a chemical is losing electrons, it's said to be oxidized. If the chemical is gaining an electron or electrons, it's said to be reduced. And yes, I know some of you are thinking, reduced, how does it mean it's gaining? Well, it's a definition we're going to have to just know. Oxidized comes from other studies in which oxygen was part of a redox reaction. We'll see later on that combustion reactions are any reaction in which oxygen takes electrons away from some other chemical. And the oxygen oxidized, there's a correlation there, and we'll see why reduce means a gain of electrons. But for right now, you just have to know oxidized, it's losing electrons. Reduced is actually gaining electrons. And just to make it more exciting, to increase your vocabulary, there's another word that means the same thing for oxidized. If something is oxidized, it means it's the reducing, wait for it, agent. If something is being reduced, it's also called the oxidizing agent. So to say something has been oxidized, it's also called the reducing agent. Yeah, you got to get that down. Flashcards. To say something is reduced, it also means it's the oxidizing agent. Reduced oxidizing agent means the same thing. And if you think about it, if it's reduced, it's gaining electrons. It's the one taking electrons. It's the bigger sun. It's the oxidizing agent. It's working on another chemical. So reduced oxidizing agent means the same thing. So let's practice what we just learned. And looking at your definitions, so here are two reactants. One of them is oxidized and one of them is reduced. So go ahead and pause the video and decide which one is being oxidized and which one's being reduced. And when you do this, you have to compare, well, here we have elemental zinc. What's happening to it? What's being formed on the other side? So is that elemental zinc losing electrons or gaining electrons? So go ahead and pause the video and decide which one is being oxidized and which one is being reduced. On the reactant side, we have elemental zinc, so we'll just emphasize it with a knot. Over here we have zinc 2+. So it lost 2 negative particles, it lost electrons. Zinc is losing electrons in this reaction, so it's being oxidized. The copper chloride compound, you have copper, the cation over here, and it's forming elemental copper. The copper is taking electrons, so it's being reduced. Okay, while you're at it, go ahead and one of them is the reducing agent and the other one is the oxidizing agent. So go ahead and pause the video and label the two reactants as reducing agent and oxidizing agent. You can memorize the definitions and know that oxidizing agent goes with whatever's being reduced. But the oxidizing agent, that's the one taking the electrons. So the oxidizing agent would be the copper chloride. The reducing agent is the one giving the electrons to something, and that would be the elemental zinc. Okay, we haven't done this yet for this type of reaction, but go ahead and try and write the complete ionic equation and the net ionic equation. So pause the video and give it a try. By the way, when you're done with the complete ionic equation, unpause and check your answer. So everything that's AQ could be changed. So the copper chloride AQ is written with its 2 ions and the zinc chloride. One note, the zinc is elemental zinc. It's still elemental zinc in the complete ionic equation. Copper on the product side is elemental copper. And I put it as elemental copper down there. And you don't have to put the knot. I just want to emphasize, don't make them into cations. If they're not cations in the normal molecular equation, they're not cations in the ionic equation. So here is our complete ionic equation. The only spectator ion in this single replacement redox reaction is the chloride. So the chloride is canceled off, and we have our net ionic equation in which elemental zinc reacts with a solvated copper cation. The copper solvated cation collides with the elemental zinc. The copper cation is able to take electrons away from elemental zinc, and I'm going to try and show this over in this diagram over here. The copper collides and forms elemental copper, Cu0. The elemental zinc loses 2 electrons, and it becomes zinc 2 plus, which becomes a solvated individual ion floating around in the solution. So if you are doing this reaction in the laboratory and you've done something very similar, if you remember our copper zinc laboratory, and that one sulfate was the spectator ion, here it's the chloride, but you added elemental zinc to your copper sulfate solution and you formed elemental copper, and the zinc seemed like it was going away, but instead of seeing all the zinc atoms as a piece of metal, they become individual zinc cations, and the reaction stopped when all the zinc reacted. One last note as far as oxidizing agents and reduced. In the molecular equation, we just grouped the chloride with the copper and said the copper chloride was being reduced. In reality, the chloride is a spectator ion, and it's just the copper 2 plus that's taking the electrons. The copper 2 plus is the oxidizing agent. It's the one being reduced, gaining the electrons. However, if I gave you a molecular equation, if you just said the copper chloride is being reduced for this particular reaction, that's fine. You don't need to worry about the spectator ions unless you're looking at the complete ionic equation or the net ionic equation. The last type of chemical reaction that I expect you to be able to predict if a reaction will happen or not are a type of redox reaction called single replacement. And the reactions we're going to study occur when a metal cation and a metal in its elemental state are mixed together. If a chemical reaction happens or not, the metal cation will take electrons away from the metal that's in its elemental state. And all the ones we're going to look at, the cation would go back to its elemental state. As far as this prediction, what information, where in the information packet are you going to find out if this occurs or not? In the information packet is a list of metals, just like the one shown on this slide. So on this slide, the list is horizontal. In the information packet, it goes vertical, and it's called the electrochemical series. And when you have a reaction, the single replacement type, this redox reaction, there's 2 metals that are involved in the process. So we have this list of metals. When they're mixed together, how to use this table to predict if one would occur or not. This list shows a lot of metals. It doesn't show every one. So if you had a test question, it would just involve these metals. But what do we notice? We notice that gold is down at the bottom of the list. And what do we know about gold? Gold is extremely inert. There's very few things in nature that gold would lose its electrons to. Metals that are down at the bottom of the list, they have a strong hold of their electrons. What about all these metals that are up here? Well, if you went looking in nature for lithium or sodium, you wouldn't find elemental sodium. Things that are up the top have a weak hold of their electrons, and they're easily taken by other chemicals. So, what does that mean as far as this chart, and if we're comparing 2 metals? So, the rule of thumb is if the metal cation is below the metal, then a reaction would happen. So let's give an example of something we've already seen in the laboratory. If you remember your copper laboratory where you added elemental zinc, so we added copper and zinc together. So here's zinc and there's copper. When we did it, we had elemental zinc and we had copper, the cation. The cation is below the atom that's in its elemental state, so a reaction occurs. Copper 2 plus the cation has a stronger pull for zinc's outermost electrons than zinc does. If you would put that copper into elemental gold, for example, so if we were comparing copper 2 plus and gold, the cation's above the atom in its elemental state. Gold has a stronger hold of its outermost electrons than the pull coming from copper the cation, so no reaction would happen if you dropped your gold ring or gold piece of jewelry into that copper sulfate blue solution that we had earlier this quarter. We could have used any other metal besides zinc. For example, we could use copper 2 plus and lead. Instead of putting elemental zinc pieces into our copper sulfate solution, we could have put lead pieces, and the cation, we have lead and we have copper, the cation is below the elemental atom, a reaction would occur. But lead's sort of toxic, so we chose something like zinc that's actually less toxic and something used in our body for our experiments. There you go. Here's how to use this chart. So let's go on to the next slide and practice using this. So let's do some practice problems. We have 3 potential redox reactions, single replacement redox type, 2 reactants, and if a reaction happens, we'll have 2 products. The first one, if we put aluminum pieces into our blue copper sulfate solution, would a reaction occur? So instead of using zinc in that one laboratory, could we have used aluminum? So let's go ahead and pause the video. Let's look at our chart, our electrochemical chart, and predict if a reaction would happen or not. So pause the video and make a prediction. So we're comparing copper to aluminum. It's copper the cation and elemental aluminum. And the cation is below the element, so a reaction will occur. So we know that a reaction will occur, and if we draw a little picture of what's happening, so you have an aqueous solution of copper cations, the spectator is sulfate. The copper cations will collide with aluminum, elemental aluminum. In all of our single replacement reactions, and this is something you just have to have memorized, if there is a reaction, the metal cation will go to its elemental state. I mean, it doesn't have to be that way, but all the ones we're going to look at, it's going to be that way. So copper 2 plus cation forms elemental copper. Aluminum, if it becomes a cation, well, there's only one ionic state it could form. So aluminum forms aluminum 3 plus, which I've kind of said it a few times. Elemental aluminum, we use it a lot. Aluminum, the cation, is actually relatively toxic. It's not a good thing to have. It's not quite as bad as having lead, but why didn't we choose aluminum? Well, it has some toxicity just like lead, so we chose zinc. Regardless of those tangents, we have our single replacement, we have 2 reactants, 2 products. The cations and the anions switch partners. It doesn't matter which one you write first, but on the product side, we're going to form elemental copper, and we're going to form aluminum, the cation, sulfate's a spectator ion. How it looks on the reactant side, a single atom and a salt, it's going to be the same thing on the product side, a single atom and a salt. So we're forming copper, and we're forming aluminum sulfate salt. Okay, it's not a 1-to-1 ratio. Aluminum 3 plus, sulfate 2 negative. We need 2 aluminums for every 3 sulfates. So that's the correct formula of that product. And again, try not to create your formulas of your products based upon the ratios over here. If there's only 1 sulfate, the reason why we have 3 sulfates to 2 aluminums is because of the charge of the ions. As far as phase labels, most metals that go to their elemental state are solids. There's only a few that aren't, but solid for copper, it's a solid at room temperature. Aluminum sulfate, is that AQ or is it a form of crystal? We could go to our solubility chart and we would find out that it's soluble, so it's AQ. But just be aware, when we do single replacement reactions, hopefully the examples that I give, the salt is AQ. I try and do that. I'm not trying to combine 2 reactions into one. We're not forming a precipitate. It's always good to check, but if you went to the solubility chart, aluminum sulfate is soluble, so AQ. Lastly, we need to balance the reaction, and we can look at it and tell it's not balanced. There's 2 aluminums on the product side, only 1 on the reactant side. So let's go through and balance the reaction. A lot of times you can just look at it. There's 3 sulfates on the product side, so you can kind of group those together. There needs to be 3 sulfates on the reactant side. So putting a 3 in front of the copper sulfate. 3 copper atoms now, so we'll put a 3 there. There's 2 aluminums on the product side, so a 2 there. So there we have it. There's our balanced chemical reaction. Okay. Go ahead and look at the silver reacting with the copper sulfate. If we drop silver pieces into our blue copper sulfate solution, would a reaction happen? So pause the video, look at your chart in the information packet, and use that to predict whether a reaction would occur or not. If a reaction occurs, go ahead and get the product formulas, balance the reaction, include phase labels. If no reaction is happening, then just write NR for no reaction. So pause the video and then see what you get. So we're comparing copper, the cation, and elemental silver. Since the cation is above, this chart tells us that there's no reaction. Silver has a stronger hold for its outermost electrons than copper, the cation. So no reaction. On our chemical reaction, you can just write NR, and that stands for no reaction. Okay, let's do the last one. Elemental lead and hydrogen cations. So we're comparing elemental lead, you can put the not there if you want. Hydrogen cations, nitrate is just a spectator ion. So you should be able to find lead and hydrogen in the information packet, so go ahead and predict if a reaction would occur or not. So with any acid, you produce the hydrogen cations. That hydrogen cation, that metal cation, is below the lead that's in its elemental state, so there will be a reaction. It means that lead's going to become a cation and hydrogen's going to go to its elemental state. And there's one thing about hydrogen when it goes to its elemental state that you just have to memorize, and I expect you to memorize it. When hydrogen goes to its elemental state, it forms H2. It's a diatomic molecule. It's a covalent element. You just have to have that memorized. Most metals, when we write them, if they're in their elemental state, it's just a single atom. For hydrogen, it's 2 hydrogens that are bonded together. And the other thing about lead, oh, that's lead. Is that lead 2 plus? Is that lead 4 plus? Which lead did we form? When we have problems like this and you have a metal that's forming a cation and you can't predict what charge it's going to form, it's not group 1, group 2, or aluminum, you will be told within the problem what charge that cation would be if it was formed. And up here in the problem, the last sentence, if lead became a cation, it's plus 2. So you need that piece of information, so 2 plus. So we have 2 reactants, we have 2 products. Go ahead and write the correct formulas for the products, write the correct phase labels, and then make sure the chemical reaction is balanced. So go ahead and pause the video, unpause when you're ready to see the answer. So shown on the right are the correct formulas for the 2 products. One other note about hydrogen, at room temperature it's a gas, so it gets the G label. Most metals in their elemental states are solids, although the other one you kind of have to know is mercury is a liquid. So we have AQ, nitrate salts for lead nitrates are all soluble. However, it's not quite balanced yet, but how would we make it balanced? Putting, there's 2 nitrates on the product side. Having 2 nitric acids react makes a complete balanced reaction. So there's our final work. Yay!
Redox reactions can happen between metals. The transfer of electrons can happen between metals. It also happens, or it could happen, with carbon-based molecules. Anytime you have a combustion reaction, that's any chemical reaction with oxygen, there's a transfer of electrons. If you don't have metals in a change of ionic state, it's a little hard to recognize if something's been oxidized or reduced. Here are 2 general rules to recognize if a carbon-based molecule has been oxidized or reduced. If you look at the reactant side and see what it forms on the product side, if the carbon-based molecule gains oxygen and or loses hydrogen, it's been oxidized. If you compare the reactant and the product has more hydrogen, it gains hydrogen or loses oxygen, it's been reduced. So let's practice these two rules in this problem down here. So you're given a carbon-based molecule of ascorbic acid. So you should look at this molecule, count how many oxygens and hydrogen it has, and look at its form on this side. And using these two rules, decide if it's been oxidized or reduced. Why don't you pause the video and unpause when you're ready to check your answer. Okay, so let's go over the answer. When you look at this, I wrote how many oxygens there is in the reactant. There's 6 oxygens, 6 hydrogens. In the carbon-based molecule on the product side, there's still 6 oxygens, so that didn't change. But the carbon-based molecule has 2 less hydrogens. So since it lost 2 hydrogens, so loses hydrogens, it was oxidized. By the way, this reaction, it's iodine, I2, it's taking electrons away from ascorbic acid, which is vitamin C.